Okay, so this little video, I'm going to go over, we're going to work out what an inverse matrix is, what a formula for an inverse matrix is. So they become really important as we work through fundamental matrices and everything that we're going to do with them. So now's a good time to talk about inverse matrices. So what I want you to do, this is your little anti-set, multiply these two matrices. As a reminder, we go across and down. So do this times this plus this times this. That would be the top row multiplied by the left column. So it would be in the top left. And then you'd go on from there. So that's going to be, top is going to be 1 times 5 plus 2 times 10. The top right, that would be top by right, is 1 times 6 plus 2 times 11. So I get 1 times 6 plus 2 times 11. And then the bottom, I'm going to get bottom row by left column. So that's 3 times 5 plus 4 times 10. 15 plus 40. And then bottom by right is going to be 3 times 6 plus 4 times 11. So that is 18 plus 44, which is, okay, I think I did my arithmetic correctly here. You get that. Okay, so next thing I want to do is define what an inverse matrix is. I may have shown this to you previously. I'm not sure. The most basic definition of an inverse matrix is that A times A inverse is the identity matrix, where if we're working in 2x2 land, the identity matrix is 1, 0, 0, 0. Whoop, undo 1. It's the identity matrix is always a square matrix. This would be I sub 2 actually. And then it has along that diagonal, top right to bottom, top left to bottom right, I've got 1s. Everywhere else there would be 0s. So for example, you may be able to follow this in your head. The 3x3 identity matrix would be 1, 0, 0. Next row, 0, 1, 0. Bottom row, 0, 0, 1. Hopefully that's okay. So the question becomes, what formula can we come up with for an identity matrix? So I'm going to do something in general, or I'm going to do something with some numbers that are like really specific, and then we're going to make a generalization. So I sort of... Okay, so to do this, I am going to look at this equation. Remember, A times A inverse is equal to the identity matrix. So I have chosen I chose prime numbers that are like they're prime, so they're unique. I won't get fooled by the math that happens with these guys. What I want to do is find I'm going to this matrix here is A. This matrix would be A inverse if I could solve for W, X, Y, and Z, because I've got the identity matrix on this side. So what I'm going to do is algebraically work out what these guys have to be in order to in order to have this system of equations be true. So my first line is going to be 3W plus 5Y is equal to 1. My next line is going to be, I'm going to do the 2 lines, so that is, let me write it out. The next line is going to be 7 5w plus 11y is equal to 0. That is the line. The first line here is this times this equals that. Or sorry, this dot product, or 5w plus 3w plus 5y is equal to 1. The other one is this row times that column, and that gives me this guy. I'm going to worry about the other ones later. So you may be like, oh man, no way, I'm not going to do that. But it's actually solvable. Let's solve for, why is it solvable? Because of easily, quote, because of this 0 right here. It makes it so that I can solve easily for like y or w, and then plug it into here, and then solve for the other one. Alright, so what I get is that w equals minus 11y over 7. Point. That would be this moved over divided by 7. Now what I can do is plug in this guy right here for that right there, and then I'll have my y's. I'll only have y's in one equation. So that gives me 3 times, I'll write negative 3 here, times 11 over 7 times y plus 5y equals 1. Now what do I need to do? I need to put this guy over a 7, right? So that gives me, it's getting messy, but it'll get good. I'm just going to write 7 times and over 7. From there, I can factor my y out and get y times negative 3 times 11 over 7 plus 7 times 5 over 7 close equals 1. Now I can divide by that thing. Yeah. Sorry. Since these are the same denominators, I could write this as, I'll do it out, y times 11, actually undo, what I'm going to do is flip these a little bit. 7 times 5 minus 3 times 11 all over 7. And that's equal to 1. Now, I'm going to divide by that thing. That's going to give me y equals. When I divide by that, or I could multiply by the reciprocal, what I'm going to get is 7 over 7 times 5 minus 3 times 11. Now, because I know where this is going, I'm going to slightly change this and write equals negative 7 over, I'm going to multiply the top and the bottom by a negative. So that gives me 3 times 11 minus 7 times 5. Now, that's what y is equal to. I am going to move this up to the top real quick. Okay, so this is where it starts to get cool if you understand some of the things that I've taught you about matrices. Look at that guy right there. That's the thing that we just solved for. That's this, which is this. Some things that I see here. Remember, A's inverse, it has to be related to A. My goal here is to figure out a formula for the inverse matrix for A, given the components. What would I do? How would the 3, the 5, the 7, and the 11 play a role in this inverse? Well, look. What's the det of this inverse? It's that product minus that product. Whoa, look at that. 3 times 11 minus 7 times 5. Maybe I should have written 5 times 7. That would have been more slick. Anyway, and then look, y right here. I've got that negative, right? So what can I do? I get y is, y, look, 7, negative, right? So what I think is that this inverse piece is related to that. I think this inverse piece is going to be the det divided by the negative version of whatever entry that is right there. If that was a 14, I would have a negative 14 over the det. If this was a 643, I would have a negative 643 over the det. So what I want you to do is figure out what W is. Remember, we had a formula here a moment ago that had W in it, and I want you to see if you can, was it this, maybe? It was. It was that 11 over 7y. See if you can figure out what W has to be. I want you to pause and actually do it. Don't just be like, oh, he's going to tell me in a moment. You should pause and figure out what W is. Hopefully you took notes earlier. If not, rewind. Okay, so I was almost right a moment ago, and I hope you caught that. W was a negative 11 over 7y. If I take a negative 11 over 7, multiply it by y, I get negative 7. The 7's cancel, the negatives cancel, leave me with the 11. The bottom det piece stays there, so I get 11. Okay? So now what I want you to do, I want you to do the same thing that I did. I did this times that column and this times that column. This times that column gave me a 1. This times that column gave me a 0. I want you to do it the other way around. The 3 times the 3 and the 5 paired with the x and the z, but that's going to give me 0. And then the 7 and the 11 paired with the x and the z, and that's going to give me the 1. So I want you to try to do that the same way that I did here. If you need to pause, rewind a little bit, and use that to help you see what to do, that's totally fine. But multiply those guys out and solve for x and z in the same way that we did. I actually do expect you to do that. So pause it. Okay, I'm going to put the answer up in a moment. Alright, so if I've done this correctly, which I think I have, then you should have this thing. What I want you to see is that the 11 and the 3 are the 11 and the 3, right? Well, the 3 and the 11, what did they do? They switched, right? And the 7 and the 5, sorry, the negative 7 here and the negative 5 here, well, those pieces stayed in their spots, but they became negative when I was finding the inverse. So what I can do here is write that a inverse is 1 over that det, 3 times 11 minus 5 times 7 times, well, the 11 is here, and the 3 is there, and the 5 goes negative, and the 7 goes negative. Now, you might remember what I said in the beginning. What I said was I chose these numbers because they're unique. And notice I never multiplied anything, I just left it, right? So my question for you is, this is A inverse. So if I gave you A equal to A, B, C, D, could you go straight to A inverse equals? What I'm saying is, if instead of a 3, a 5, a 7, and 11, I gave you some variables, right? We figured out that this is the inverse of that thing, right? And maybe it makes sense to multiply these to make sure well, maybe we'll do it with the A's, the B's, and the C's. But if I go to the 3, the 5, the 7, and the 11, and I can look at a pattern and see what happened here. let me just change those to A's, B's, C's, and D's. What would A inverse be? So see if you can think about that and figure it out and write it out right now before I do. Hit pause. So it's 1 over, the deet is A, oops, that looks like a D, A, D minus, you can write B, C, times, let's scooch over. What happens? The A and the D switch, so I get D and an A, and then the B and the C become negative. Minus B minus C. If you Google the formula for the inverse of a 2 by 2 matrix, that's the formula you're going to see right there. You switch the two, the A and the D, and you negate the B and the C. The way that I remember it is that like the A and D, like those letters just like sort of look similar to me. They're almost the same. The D just goes up a little bit higher, right? So they're similar. So what do? They are the ones that switch. Whoop! And then these guys get negated. So hopefully you're cool with that. And now what I want to do is convince you that it has to be true if you're not totally sure. Remember, we said that if I've got A times A inverse, it has to give me the identity. So let's do A times A inverse as we have it written down here. I'm going to 1 over AD minus BC times A B, C, D, D, A minus B minus C. All I did was move this out front. I'm multiplying this by that block. This is a scalar. That's totally legitimate for me to move that out. Remember, what do I want this to be? I want this to be the 2 by 2 identity. So we can do this pretty quickly. It is 1 over AD minus BC times big long matrix. It's still 2 by 2. I just need a lot of space. I got this product times, this row times that column. That gives me AD minus BC. Notice that is the same. I must have pressed pause somewhere. I don't know where. Anyway, multiply these guys. It's totally legitimate to take this guy and move it out front. It's a scalar. Then I multiply this row by that column. Notice it gives me A times D, that's AD, minus B times C. Boom, that's 1. So I encourage you to do the rest of that multiplication, and I'll hit pause, or you hit pause, do the multiplication, I'll write it out, and hopefully we're good. Okay, so in this column, or in this entry right here, I get minus AB, plus AB, that gives me 0. Here, gives me 0. Here, gives me the same thing as what I had there, so I wind up getting a 1. So, woohoo, it does work. Alright, so I think 2 more things that I want to say about an inverse matrix in this formula right here. One is that I can use this with functions a lot of the time. For example, say A was e to the t, C was 10 e to the t, B was e to the negative t, and D was 4 e to the negative t. I'm just making things up. I could apply this and it would still work, which is really cool because we did it with variables, but it works with most functions as well. Secondly, this is the determinant, right? So it turns out that not all matrices have inverses. Some matrices, there's nothing that I can multiply it by to get the identity matrix. So the way that we can determine that is by looking at the determinant of that matrix. if the determinant, if this denominator is 0, then this thing is cool. If this denominator is 0, then I get a 1 over a 0, and it doesn't work. I can't have things over 0 in math. It just doesn't exist, right? So A inverse exists if the det is non-zero. So if det of A is non-zero, then A inverse exists. And that's a theorem probably from linear algebra or something like that. But hopefully you're good with this. This is a long video, but these matrices, these inverse matrices, become important for us, and I wanted you to understand why this formula is what it is. I could have just told you the formula in 10 seconds and been like, all right, we're good. But I really wanted you to see why this is true.